Hello, guys. So, welcome back to the series. And last time we actually looked at activation functions. And I promised you that we will build a neural network that will have two hidden layers in this context and three inputs. And the goal will be to predict taxi fares in the New York City. So, in this video, I will show you how to build it using TensorFlow, Keras, and I will also go a little bit through the error functions and why we choose the different error functions. So yeah, let's get to work. So as usual, I will use my remarkable here taxi prediction. And first thing I think of here is data. Where is the data? So in our case, the data is located in GitHub here. So you see, this is basically a CSV file. It could have been. This is from Kaggle. Usually, you have a lot of 50,000 rows, and you can break them down and clean them up. But the data is here as a CSV file, and I will get it using Python. So pandas is something you should learn if you look if you're looking to work with neural networks or machine learning. And here I just get the URL and I get the pd.read.csv, put in the URL and parse the date so that we know it's formatted as dates. First things first, always check how your data looks, and df.head is always the best, for me at least. And the default is 5, so you get 5 columns. And I will run this with 5 and run it again with 10 so that you can see. And remember, the first time I did this, I was like, oh, it's 4, but indexing starts from 5, from 0. So let's get the first 10 ones and just study the data and look at how it looks. So we have a key column here, we have the fair amount at least, and pick up date that looks like quite weird, but okay. And we have the longitude, latitude, and the drop off longitude and latitude. And then we have the number of passengers in the car. This doesn't make a lot of difference, to be honest, because the, no matter how many people are in the car, the price will still be the same unless the people decide to split up the the fares. And but that's not what we are looking at here. So we are just going to look at the prices and assume that each trip will be for itself, so we're not splitting the fares. And the next thing is feature engineering. So when you get the data, it will usually not be in the format that you want, so you have to do some feature engineering and pre-processing. So now we are in this phase. Let's clean up this data and make it processable for our neural network or machine learning model. So if you want less data, you could actually just, as you can see here, you have one, 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 and you can do this actually filtering it by the passenger count equals one if you want it to be down to the number of passengers. But I don't want that, so I just let that be. You can try it later in this notebook. And on the other hand, you can also drop other columns that you don't need. So here we don't need the key column, we don't need the passenger count because it's not something I care about now. And axis one just means that we drop the column. So let's look at it again. That's it. You see we have the fair amount and latitude and longitude. And shape is another really good function which gives us these are the rows, sorry, and the columns. So one, two, three, four, five, six columns plus this one. So gives you 6 and you have 555, around 55,000 rows. So let's do some quick math. We want to make sure that we get the date and time because we will actually be getting the day and the hours of the day from the pickup date and time. So the we will use dt.weekday, which gives you the series of the weekday, and then we get the hours, which gives us the hours of the day. So 0 is Monday and 6 is Sunday in this case. And then the fun part where we calculate the distances actually using the Pythagoras, and we apply this theorem, which is should know this by now. And if you don't know this, go back and check because it's just the hypotenuse we're trying to get here. So we get the x of the drop off longitude and the pickup longitude, and then we get the difference between the drop off latitude and the drop off the pickup latitude and multiply it by the degrees. And then we do the Pythagoras here and apply the square root, we get the distance. And from there, we actually drop all the original values. So we drop this one, we drop all these values and insert the new values. So we'll not insert, but we already have saved it as distance. And we filter based on distance and fair amount. So that's what we are doing here. And as you can see here, we have the fair amount, we have the day of the week, we have the pickup time, which is this is what 3 p.m. and the distance in miles. So this is in a shape that we actually want to use going ahead. So let me run this with you. There, there, looks good, and the DF shape still looks good. And another really good function is the DF, sorry, the data frame describe, and this will describe all the mean, the standard deviation, the minimum, the maximum in all the different. And the count makes sense because these are the rows. And as you can see here, the maximum is 49 for the fair, and the minimum is 2.5. So that's it for here. And I love the df dot correlation, which actually gives you a view of the data. So if you know what correlation is, if two values rise together, this is they are positively correlated. And if the correlation is zero, it means that there is no correlation. And if they're negatively correlated, one increases and the other one decreases. So let's look at the fair amount and distance. You see, this is quite a high number. So 0.84, it makes sense because the more you drive, the more you will pay. If unless there is a really special taxi company that doesn't make you pay more for more miles, then I would love to be a usual customer for that company because then I will be saving a lot. But study this, try to understand the different connections and correlations here. Next, we will build the model. So very simple model. I would call it simple because we are just using the out of the box sequential model, and we just add some fully connected layers. So let me draw it for you. Now we have pre-processed the data, we have studied it, and we are ready to put it in the model. So what we will do now is pick or build the model. And this is where the fun part starts. So what we will do now is we have three inputs, x1, x2, and x3. This one is time of the day, and this is the weekday. And the last one is the miles you will be traveling. And then we have the first hidden layer. So this layer will be, I cannot draw 512 neurons, but you get what I mean. So we go down here, 512 neurons. From our last video, you remember what a neuron does. A neuron takes the weights, multiply it by the inputs, and adds the bias for all the different weights here. So fully connected means that each of these inputs are connected to all the neurons here. So that's the first layer, and we are using the rectified linear unit activation function. And then we have another hidden layer, and this hidden layer now gets the input from the first hidden layer, and we make this also 512 neurons. And it does a neuron does the same thing here too. So multiplications will be the same, and we have the rectified linear unit as the activation function. And when it's all done, we will actually get the price, fair price for your taxi trip. Woohoo! And you will get to know what you're going to pay based on the historic data or the data that we have trained the model on. So we will make some important decisions here. So we have two hidden layers. One of the more important decisions is the epochs. So this is how many iterations your model will train. So if you, let's say we choose 20 iterations just to start with, it means the training data will run through this neural network 20 times. Means also that back propagation will happen 20 times. So that is the number of epochs, how many times you train the model in this one here. And then we have to choose the optimizer. We have not covered this yet, but in this case, we choose the optimizer Adam, and we have to choose the loss. We will look deeper into the loss quite soon. And in this context, we use mean average squared, mean average estimate, of course. And that's it. We do the model summary. So we have chosen the optimizer, we have chosen the loss function and the activation functions and the number of hidden layers, and the bias will be initialized as 0 in this case, and then they will be back propagated to the right values. So in Python and TensorFlow and Keras, you will be building with model sequential, which means we stack the layers one after the other, and then we add the dense layer. A dense layer means fully connected layer in this case with 512 neurons, and the activation is ReLU, and the input shape is the three variables, the three inputs that we have. Do the same, but here we don't have input because the input is the input from this layer. And the last layer, which is the output layer, is only one output, so we have one neuron. And this is kind of a regression problem, and we don't need many outputs. We are just trying to predict the number, and we compile the model with the Adam optimizer and the loss, and we get the metrics for the loss. Using this model.summary, this will give you all the trainable parameters. It will give you where the parameters are. As you can see here, with this small model, we have almost 260, we have 265,000 trainable parameters, which gives us a lot of knobs to actually turn and play with. And with that done, we have created the model architecture and we have chosen the optimizer and the loss function. Now we are going to split the dataset. So we split the dataset into training split and validation split. This is quite easily done, to be honest, with the model.fit, where we have X and Y. As you can see here, we have X and Y, and we have the validation split, which means that 80% of the data will be used to train and 20% will be used to validate that our training actually worked. So think of this as an exam, and you are studying for the exam. And when you get and validation, when you're training the model is like you're studying for the exam. So 80% in this case, and the validation is like taking the practice test using the small part of the material that you actually did not study, the 20%. And this is to avoid overfitting. And we'll look at this now. So when we train the model, it actually goes through the different epochs, and this will actually continue until the last number of epoch, and you can see the loss, the training loss, and the validation loss. So 3 different days, and found out there will be 3 different prices, which makes sense with the taxi prices if you think about how many people actually move around on Friday and Saturday compared to Monday. And we train this using TensorFlow and Keras, and use the sequential model. So here we just stack everything after the other. So let's look closely at this mean absolute error, which is the loss function we are using, and why we are using this loss function. Let me show you here. So I have this other Google Colab notebook where I'm going through all these different computational error computation in neural networks. So the mean squared error is just very simple and easy to understand. As you can see here, you have 1 divided by the number of training examples, and then you subtract the difference from the actual values and the predicted value, and sum them all and square everything. It's that easy. But we have some some problems here because it is very sensitive to outliers. As you can see, you multiply the outliers, the error in the outliers. So this is good. It's primarily used for regression problems, and you want to predict a continuous value. And then you have the root mean squared error, which has the same unit as the target variable, and it makes it more interpretable than mean squared error. It's also still sensitive to outliers because we are taking the power, the difference from the actual value to the predicted value is in the power of 2. So still sensitive and used in regression problems. The mean absolute error, which we used, is a little bit less sensitive to outliers because we are not taking the power of 2, we are not squaring it, but we are actually just taking the absolute difference between the predicted and the true values. So this is less sensitive to outliers, and it provides a linear penalty for errors. And then we have the, I would say, cross entropy first, because can be used both in binary in terms of when we have only one. Binary is when we have only two outputs usually, and it's either true or false. So this can be classifying spam, or it can be. This is when you have two outputs, so used for binary classification problems, as you can see here. And the next one is categorical cross entropy. So this is where you have actually multi-class classification problems. This can be you have 10 pictures and you want to classify you want to find the loss in the different classifications. This is the one you use. So the math is something you will understand more and more when you start applying these functions. But what I think you should do in the beginning is just applying them and checking and testing them differently. So here we applied mean absolute error, and we got a loss of, let's say, validation loss of 2.309. This means that the value that we predicted is in the range of $2.3 in the range price of $2.3. So it can go up or down by $2.3. So seems not that bad, to be honest, to using this in this scenario. And we actually only used 20 epochs. We only trained 20 times, or we the model went 20 times through the training set. And for the batch size, we could have tested it in different batch sizes, and we could have 50. We could have had different batch sizes here, and other things you could have done to try and improve the accuracy is actually changing the number of neurons. And you could also remove this layer and have only one layer. So these are things you should actually try out and test to see what works for your uh, for your case. So today the topic was just creating your first neural network using TensorFlow and Keras. That you have done. It's a sequential neural network with two hidden layers and 512 neurons in each of the hidden layers. And you have one output which predicts the fare. So, and then we've looked into the different error functions, and it's crucial. This is very crucial step in the training process because it actually quantifies how far the predictions are actually from the target values. So this is something you should look at a lot, and this is also called the loss or the cost function. And when we come to back propagation, we will see how this is used to find the perfect, not the perfect, but the best values for the weights and the biases or the parameters of the model through going backwards in your neural network. And that's it for today, guys. I hope you learned something. And if there is anything in this video that is incorrect, please put in the comments. And anything you want me to cover, please also put it in the comments. But the next thing I will cover is back propagation and how it works and why it works. So see you next time, guys.